So today we're going to talk about HyperLynx PI and my big rock analysis that we can run on this design. And the reason I call it big rock is it's not sign off. It's making assumptions. They're good assumptions, but it's just making assumptions. And let me show you. So if we bring up our flip chip form, we go to our DRC. Here's HyperLynx PI. So when it comes up, the first thing it does is it populates the forms with all the nets that go to more than 10 pins. So you can up this number or lower this number to see more or less nets in this section. Now as you go through the nets, like this no connect net, I'm going to hit it to N, which means don't include it in the simulation. The other thing you might notice is under the voltage, it does have some smarts in it that if it starts with a V and it has an underscore and then a number, P, a number, it pulls that out and it says, oh, you must be 1.8 volts. Now down here at the bottom, this one didn't have a underscore in it, so I actually changed that. I actually went in here and I typed 1.8 in the last time when I ran this, and it does remember everything in the form. The other thing you can do is you could export all this value and you can import it back in, but it does remember what you have, so you don't have to do that all the time. So up top, we can lower or raise how many pins we want to see. The next option is, by default, what this comes in is 17 milliamps per die pin. So if I hit calculate, it goes off and figures out the current draw. You know, we're doing a power analysis, so empirically a die pin draws 17 milliamps. So it's just empirical data. You can change that and you can make it like 25 milliamps per die pin, make them a little bit hotter, and it changes the current draw. Now, why I call it big rock is we're not setting each die and each pin on each die with the amount of current that each one draws. We're just making a general assumption that all pins are running at 25 milliamps. Now, you can go in and you can absolutely tell each pin what current you want to do, but that's not big rock analysis. That's not the quick setup and everything. That's actually going into the tool and driving the tool and setting up the models. Part of the big rock setup is it's making all the models for you based off of this number. So the last part in here is we tell it the error limits, or what do we want to see when the voltage drops below 5% of the voltage, like 1 volt or 1.8 volts, or the max current density is more than 330 amps per square millimeter, or the max current of a via is 1 amp. So if you have a via that has 1 amp going through it, I want to see that. And then the last one, I just added this not too long for another customer. They actually wanted to run the simulation at a different temperature. It's part of the batch. I didn't have it part of the form, but I was just hard coding it. But now I brought it out so you can actually change the temperature. So that's all good. So we have all this set up. Now what we need to do is we can run it. So when we run it, we just hit this PI up here. What it does is it exports the database, as we have it right here, to HyperLynx PI. And, you know, I'm just clicking once. So from here on, I'm not clicking anything. It's exporting the database. Once that's done, it kicks off HyperLynx PI. HyperLynx PI comes up and it loads up the database. So this is all automatic. The next step it will do is it will start running the batch simulations for all the nets that we checked yes for inside the form. So I'll just let this go ahead and come up because it's still loading the database right now. Now it's loading all the copper pore areas. And you don't want to hit that end script up top. That's actually the box that's talking back to Xpedition. So now we've got the design loaded. We're starting to run our DC simulations on the nets that we have picked. And you can see the 5%, 330, 1000 in the forms, in the form right here that we passed it. So we passed it that as a one value that all nets get adhered to. And as you can see, you can change that. You know, if it wasn't big rock, you could go in and change that per rail if you wanted to, but we just made it simple and said, hey, let's create the models for you, and we're going to run against these values right here. So now it's going off and running its DC simulations. And I think this entire process, when I ran it before, takes about 10 minutes. So what I'm going to do is I'm going to pause the video, and when it comes back, I'm going to unpause it, and I'll show you the results and what we have in there. So here we go. So it's just finished up. It's been about 7 or 8 minutes or something like that. So it just finished up, and it's generating the report for us right now. And you know, you'll see some flashy flashes with the waveforms and everything coming in. You know, I included the checkbox right here. It says create power scope data. So with that on, it creates all these power scopes for us for each one of the nets, so we can go poke at them and reference them as we go through the design. But the HTML is actually a pretty nice report to go through, and you can get it from Xpedition later on if you happen to close it. But let's just go ahead and let this finish. And then it closed HyperLynx. The batch is done. So now the one click that I did, it's finally finished. And if we look in here now, if we don't have the net completely routed and things, you might get something like this where no VRMs found in it. But in this case, like for DVSS, we got fail, fail, fail. This one's pass, pass, pass. So on any of these, you can go off and click on them, and it will launch the power scope. So this one happened to be the max voltage drop was, you know, 5%, and it says, oh, it had 100% voltage drop in here. So we can kind of go off and look at the data. If you go to the layer options, I can turn off different layers, and I can kind of see where the violations are. And it happens to be, you know, I have one ball pad in there that's doing it. So this is a quick summary. You can click on any of these at any time and get the waveform up. But what really kicks in is, I'm going to tuck this away. Once this is done, I just click down at the bottom and say update batch errors. So now we're looking at this within a perspective of Xpedition. So this shadow mode, let me go ahead and make this a little smaller. So this shadow mode turns everything in Xpedition gray. If I turn this off, it's back to the way it, you know, the way it used to be. Now everything's gray. The reason it does that is if I click on DVSS, it highlights DVSS and takes me, you know, basically puts a little marker on here. You can see the little X marker on there. That, hey, you have a problem in this area. And what it's telling me is, you know, what layer it's the ball pad on AH1 is what it's actually looking at. So I think what it's looking at right here is you have this internal part coming up, and we come up again. And oh, look, we have a 4 to 6 via, but yet this came up to a plane, but this plane doesn't go anywhere. So if we ran hazards, it would have, you know, this would have said this was an incomplete net. So basically it's telling us in this case that you have a pin that's not tied to anything. So it's, you know, it's basically being starved of the voltage, and it says 100% in here. So it's 100% voltage drop because it didn't get any voltage at all. So these are all DVSS. It looks like that's not complete. Let's look at this one. This one's VDD logic. So if we double click on that, it goes in and shows us the waveform, and real quickly I can see that it's on layer RDL1T. So that's the layer I'm on, and it's in the bottom left of the design. So let's move this out of the way and move this out of the way. And let's see, RDL1T is right there. So we're looking at a voltage drop basically of this via going down to you know, our part. Wait, where is it? Oh, that's a 3 to 4. So was that a via? Oh, it's voltage drop on ball pad A1 Q20. So A1 Q20. Where's my little marker here? Let me unhighlight everything. Oh, there's my marker. I couldn't see it in here. So my marker is on this pin right here. So if I double click on it again, it should highlight the net for us. And let's see, it's that pin right there. So if we follow it up and follow it up, it does have a connection, you know, to 3 to 4. And it's going over, and it's part of this rail system right inside of here. So what that's saying is basically you have a voltage drop on that pin. So if we come over and look at our design, sorry, I had to cough. So if we look on our design and do the 3D on it, and let's zoom out a little bit, we can, it's kind of hard to see in here. But you can see this pin is really dropping off from everything else inside of here. So it's getting routed out. So I can see this on there. So it's this pin. Let's go down to 6. It's not making sense to me, because on this it looks like there's a longer run going down to it, but I'm not necessarily seeing it over here. So you know, it's not my design either. I'm kind of poking at this. So there's the part on 6, 5, 4, 3. So we just have a little route on this layer. Is that? Oh. It's talking about this guy over here again. I'm sorry. Let's go ahead and look at it from the top view. And it is that pin. It's that guy over there again. It's getting routed out to it. So, you know, my bad. But the main thing is, as you go down through this, it shows you what passed. If it passes, it's green. If it fails, if it's 100%, probably didn't get any power going to it at all. Here's a current density on this VDD SRAM. That's probably a good one to go look at. And if we turn on the 3D, we can see that as we're routing this net going over, we're actually getting a current density issue with that VDD, probably because of the really skinny traces. You know, that they need to be beefed up or something like that. So we're looking at this net, and if we look at it, let me move that out of the way. It's complaining. It puts a little X on there for us. The little X is right here, and it's saying this part of it has a current density issue. And the reason it's probably doing that is it's coming from the ball pad. It's coming up and getting fed. So current density being a power routing through this trace, it just didn't like that at all, the current density. And let's see here. Here's a voltage drop 100%. Voltage drop. Oh, here's a via current. So let's go ahead and take a look at this one. So RDL 12_B. These two vias in, well, mainly this via, but this other via is red as well, are both have overcurrent. So let's go take a look at that. RTL 2_B, correct? Yeah, so these ones right here, these two vias are overcurrent. So in relationship to, you know, bringing this back in, yes, we did a big rock analysis where we assumed all pins draw 25 milliamps, and we have one set of voltages and rails to test everything against. And, you know, once we do that, we can come down here and see what each of the rails did, kind of go off and poke at them. Even if they passed, it tells you what they passed with. So here, there's a via current on this VDD logic. it's a little less than 1 amp. It's 7 milliamps or 6 milliamps less than 1 amp. So if you wanted to go off and look at that and you're like, wow, that is really close to what I set as a limit, yet it's green because it's not 1 amp, you know, it's less than that. So, you know, it's up to you to go off and take a look at these vias and these things that may be green, but it's really close to what we were looking at inside the design. So here's the one that if you click on the open batch report, it opens the DC report back up, so you can go off and look at the DC report again if it got closed or something like that. But all this data basically from here gets dumped into this form for Xpedition, and you know, you just double click on something and it will bring up the power scope for you. You click on the 3D button, you can see everything in 3D. You know, however, you know, you want to look at it, you go to the visual options. We're looking at the current density. If we want to look at the via current, we go there. If we want to look at the current vectors, we go there. If we want to look at the voltage drop across it, we can look at it in perspective by looking at it here. So those usually take you to the correct one. You know, whatever you're looking at beginning, like current density, it will take you to the correct one. And then in the layers, you can add your other layers back in if you want to see them all together. But by default, it's going to just give you on current density the layer that's having the actual problem. But sometimes you want to, you know, turn more layers on. You can go to visual options and say, oh, now let's look at our voltage drop, and we can see the whole tree for this net as we're going down, that we're picking up all the BGA balls, and as we're coming down, fanning out to the die, we have this one outlier. So the 3D view does come in handy. But if you have any questions on this, you can absolutely give me a call, let me know, and you know, we can go from there. Thank you.